Okay, so we're doing 5.5, which is Trig Identities. So trig identities are something that kids either love or they hate. I like them. They're like puzzles. It's like trying to solve a puzzle, but the problem is they're all different. They're all completely unique, and there's no way I can just say follow steps 1 through 3 and you get the right answer each time. They're always different. My daughter wanted to watch my lessons on YouTube because she's so excited that I had a YouTube channel. And I realized I was hitting the mic every time. So, sorry about that. I'll try not to do that. And I realize it's also a very boring video, but what are you supposed to do? In your textbook, page 309, you can look at those identities as a reference. So it'll make sense in a little while what I mean by what identities are. So, identity is showing that one thing is equal to another. We're proving that this is true. They're telling me that sine squared theta plus cos squared theta is equal to 1. And I need to prove that it is true. Okay, I can't say that it's not true. They're telling me it is, and I need to prove that it is true. So there are different ways to go about questions like this. There are also different strategies that you can use, and I'll review at the end. So one strategy is you can take the values of sine theta and cos theta that we did before, like this, from the terminal arm and all that stuff. We found that sine theta was y over r. You can also say that cos theta is x over r. So this is an identity. This is something that's true, something that we have already previously stated is a fact. So we can use this to now solve the identity that we have in front of us. We can substitute things in. So sine squared theta means we can take sine theta and square it. So I'm going to write this out the long way. And I'm working on the left side. So I'm going to state I'm working on the left side. I'm going to rewrite that. And I wouldn't do this step normally, but I just want to make sure you understand. Sine squared theta is another way of saying sine theta squared. Okay, it's just an easier way for us to write it. We put the squared symbol here because we want to make sure that we know it's the whole thing squared. If you put the squared symbol next to the angle, that means you're squaring the angle, not the entire ratio. So I'm going to replace sine theta with our letters, y and r. And cos is x over r, and it's squared. So I have y squared plus x squared, and on the bottom we have r squared. Our common denominator would be r squared. Now, I get to this point, and what I have to do is try to get this left side to look like the right side, and right side is 1. So right now it doesn't look like 1. And then I'm going to use my memory and the things I've learned and remember that x squared plus y squared is equal to r squared. It's the equation of a circle. It's what we did before with Pythagorean theorem to solve for the radius. So that means that the numerator is equal to r squared. And r squared over r squared is 1. So what we did here is we proved that the left side is equal to the right side. So we proved the identity. Now there's other ways that we can go about this. There's not always one single way that you can prove an identity, but this is one way that we did this. So usually if I have one of the identities that's on the identity sheet, page 309, one of those basic ones that we will be using over and over again. If it asks me to prove one of those, then I'm usually going to go this route with y over r and x over r to try to prove it. There are other ways. You can try those. Once we get through a couple more examples, maybe you'll understand them. So let's go to the next one. So again, you can just pause the video if you need to and write down the question or whatever you need to do at any time. Or you can watch it at 2 times speed so it's not as boring. All right, so I want to prove that the left side is equal to the right side. That 1 plus cotangent squared is equal to cosecant squared. It also says state the restrictions, which I'll talk about at the end. So I usually pick the side that has more things going on, that looks a little more complicated. Sometimes it's obvious, it's very more complicated, sometimes it's not. And sometimes you'll have to do something to both sides to try to get it the same. So this side, or this question, I have 1 plus cotangent squared theta. It just has a little more going on than the other side. So I'm going to choose that. So I'm going to write ls to show that I'm working on the left side. And I'm going to rewrite the left side exactly as it is. I'm not going to start work yet. I have to rewrite it. Now I'm going to start working on it. So one of the strategies with identities is if you have anything that's not sine or cos, you use your identities to change it to sine or cos. So for instance, cotangent is the same thing as 1 over tan. But we also know that tangent is equal to sine over cos. And this is just from your identity sheet. Now you could use the letters y, r, x, r, and all that to prove this, that it is tan, or you can just trust that the sheet is right. So if tan theta is sine over cos, that means cotangent theta would be the reciprocal of that. So knowing this, and this is all in your identity sheet, it's not, you didn't have to write it out. I'm going to replace cotangent with cos and sine. So instead of cotangent squared theta, it's going to be cos theta over sine theta squared. But I would write it like this. Now, I want to get it to look like the right side. Somehow this needs to change to be cosecant squared theta. So another strategy, first was changing it from cotangent to sine and cos. Another strategy is to get a common denominator. So if you have two things, put them together. So this is 1, and my denominator is sine squared theta. So I'm going to multiply by sine squared theta. Top and bottom. So now I have sine squared theta, and I have my common denominator of sine squared theta, and I'm adding cos squared theta. All right, so we have our common denominator, which is here. That's sine squared theta because it's times 1, and we're adding cos squared theta. Okay, so now if I look at my identities, I see that there's one called the Pythagorean identity. Sine squared theta plus cos squared theta is equal to 1. And that's also what we proved in example 1. So that's an identity that I can use. So since I know that this is equal to 1, I can replace it or substitute it with 1. I'm not quite there, but I'm simplifying, I'm changing things. I'm trying to get it to look like cosecant squared theta. And the thing is, cosecant squared, or cosecant, is the reciprocal of sine. So we've done it. This is cosecant squared theta, because 1 over sine squared theta is this. So we have proven that the left side is equal to the right side. Now, sometimes this is an identity, it says factor. And the reason is that sometimes you'll have to multiply, simplify, factor in order to cancel things out or to prove your identity. So when you're doing identities, you're using all the things that you've done before since grade 9. Factoring, expanding, like terms, all that kind of stuff. And you're going to use it all in some of these identities. So if I'm factoring this, I try to imagine it as if it was a quadratic like that. So instead of sine squared theta, it's just x squared. Right? So if I was to factor this, it wouldn't be so difficult. I got x and x, I got 1 and 1, but I want negative 2 in the middle, so I'm going to make them both negative. So I would have x minus 1 times x minus 1, or x minus 1 squared. So that's the same process I'm going to use. It's just now I have, instead of x, I have sine. So sine squared theta is sine theta times sine theta, just like x times x. Negative 1 times negative 1 gives me 1 in the middle. And when I cross multiply, I get negative 2 sine theta, just like I got negative 2x. So if I factor this, I get sine theta minus 1, or sine theta minus 1 squared. So how this might help me is if I was doing an identity, I might be able to cancel out a sine theta minus 1 on the top and the bottom, just to simplify it. Okay, so when you factor, think about all the things that we did before in factoring. Look for greatest common factor, look for difference of squares, look for a quadratic, look for perfect square trinomials, things like that. So just like you can factor, you can also expand and simplify. So you could FOIL this out or multiply the binomials by expanding. You could also see that I have sin x, cos x, plus minus. So it's a difference of squares. So I can multiply this out like I would by distributing and FOILing. Or I can use the difference of squares to do it a little faster. So it would be sine squared x minus cos squared x. And then I didn't touch the 2 cos squared x at the back there. So we multiplied it out. Now, just like if I'm adding x squared plus 2x squared or whatever, I can take like terms and add and subtract them. So cos squared x and cos squared x, those are like terms. So I can add these up. So negative 1 cos squared x plus 2 cos squared x means 1 cos squared x. But as we saw in our identities, sine squared x plus cos squared x is 1. So that's simplifying. Sometimes you'll have to simplify. Once you've expanded, you got to simplify. Then you might have to factor again. Like, it just depends on the situation. But these are all tools that you need to bring into every single identity you try to prove. Okay, so we got 2 more. The last one is the hardest one. Let's see this one now. When I approach an identity, so I haven't done these yet. I wrote them down, but I didn't actually do it. I don't necessarily know if I'm going to do it properly the first time or if I have to start over or what's going to happen. So sometimes you have to try things. If it doesn't work out, you try something else. You start over again. It's a puzzle. So sometimes puzzles don't work out the first time you do it. If you're doing a Rubik's Cube, sometimes you got to start over. So for me, I would look at this and I see that the left side has to the power 4. That seems a little more complicated than the right side. So I'm going to start with the left side. Maybe I have to do both. I don't know. Okay, that's terrible writing. Do it again. All right, so now on the left side, I have these things. And you notice I didn't put equals the other side. I just have the left side only. So you can't rearrange the equation. You can't take things from this side and bring it to that side and all that. You're trying to prove that this side is equal to that side. So they have to stay separate. Okay, you can't rearrange an equation. Because you're not solving for anything here. All right, so I look at this and I think, I try to factor or simplify if I can. I can't simplify, they're not like terms, so I gotta try to factor here. And I have a perfect square minus a perfect square. So this is a difference of squares. So the sine squared theta plus cos squared theta times sine squared theta minus cos squared theta. All right, so I do that. Now I think, oh, what else can I do? I'm trying to make it look like sine squared theta minus cos squared theta, which we have here. So that's great. But I need to get rid of this because that's not on the right side. Now, the good thing is that's an identity. Sine squared theta plus cos squared theta is 1. It's the Pythagorean identity. So that's it. Left side equals right side. We've proven that identity. And I just realized I forgot to do something in one of the other questions. So I'm going to go back to question 2, I think. Yeah, state restrictions. Okay. So question 2 was this one here, where we had 1 over sine squared theta, and then that was equal to cosecant theta. It says state the restrictions. So let's do that over here. Cosecant theta is the same thing as 1 over sine theta. So if you are looking for restrictions, that means that the denominator can't be equal to 0. So basically, when is this thing undefined? So some angle would make cosecant theta undefined. Now, that's going to happen whenever sine theta is equal to 0. So that's what you're thinking about. So there's only 4 chances for it to be 0. from 0 to 360. The cardinal direction. So 0, 90, 180, 270, or 360. So you'll memorize these eventually, and especially after the next unit, you'll memorize them. But you just have to test them out until you do memorize them. So you're going to take the sine of 0, the sine of 90, the sine of 180, 270, and 360, and you're going to figure out what it's equal to. So the sine of 0, sine of 0 degrees, the sine of 90 degrees, and so on. And whenever that's equal to 0, that would be a restriction on our identity. So if it was cos, then you do cos. So it's only going to be these numbers, these values. Nothing in between is ever going to give you a restriction. Okay, so 0, 90, 180, 270, or 360. So the sine of 0 is 0. I just know that. The sine of 90 is 1. The sine of 180 is 0, negative 1, and 0. So that means our restrictions are when sine is 0, sine of 0, sine of 180, and sine of 360. So theta cannot equal 0, 180, or 360. Okay, so that's what you're looking for, restrictions. What would make that denominator equal to 0? Okay, so again, pause if you need to. I will go back to the last one now. Okay, so we're going to do this one, which is more complicated. Has lots of stuff going on. Just looking at it, I'll probably have to do something to both sides. But these are the steps that we're going to be looking at here. Not in any order. I put 1, 2, 3, but the order can be in any order. So some strategies, you're going to try to factor or simplify. You want to rewrite anything in terms of sine or cos. So if you have tan, change it to sine over cos. If you have secant, change it to 1 over cos. Right? So use the reciprocal identities and the quotient identities to change everything to sine or cos when possible. Start with the more complicated side. If it's necessary, get a common denominator. And if you have something that you can separate into fractions, so 2 different fractions, then sometimes that helps. So for instance, I'm going to erase this in a second, but let's say you had sine theta plus 1. And that was over cos theta. Well, I could separate this into sine theta over cos plus 1 over cos theta. It means the same thing. And then that would be tan theta plus secant theta. Now, as it is, it doesn't make any sense, but just maybe the right side was this. Maybe this was the right side and that was the left side. So sometimes separating into separate fractions helps you get the identity, helps you prove the identity. Okay. So let's start this one. Again, it's a more complicated one. I have no idea how I'm going to do it right now, but the left side looks like it's got more going on, so I'm going to start with the left side. So I'm going to rewrite it. And it looks like a quadratic, something like a factor, but the problem is I have sine and cos in there. Sine at the beginning, cos in the middle. So I want to change that so that I only have either cos or only sine. So the Pythagorean identity is one you're going to get familiar with, because not only can you use it in this form, but you can also rearrange it to solve for other things. So if I rearrange that equation to solve for sine, that means that sine squared theta is 1 minus cos squared theta. And I could do the same thing for cos squared theta. Let's say I want to replace cos squared theta in something. That's equal to 1 minus sine theta. So in this case, I'm going to take that sine squared theta and replace it with 1 minus cos squared theta. And the reason I'm doing that is I'll be left with a quadratic still. Oops, 3. I'll be left with a quadratic. What was I doing? That's what happens when I talk and write at the same time. Okay, so the reason I'm replacing this with that is I still wanted to have something squared there, because I know I should be able to factor this. That's probably what's going to happen next. And that just comes with experience. You just practice enough, and you'll kind of see what the next step is going to be. So I'm not going to replace with, cos or anything like that. I want to get cos in there, right? This is already sine. I want to change it to cos. So I changed it there, and I knew I was going to get a cos squared. So now that we've done that, I'm going to simplify. So negative cos, I have brackets there, but I don't need the brackets. So negative cos squared theta is negative cos squared theta. No other like terms. It's nothing like the 2 cos theta, but then I have 1 minus 1, so that's 0. It's gone. Again, on the bottom, negative cos squared theta plus 3 cos theta minus 2. And I have totally forgotten what the right side is right now. I have no idea. So your goal is to get it to be equal to the right side, but usually you're just going to have to just factor and do a whole bunch of stuff, simplify as much as possible, and then check in on the right side and see, okay, am I getting close to that, or did I get there already? Like you're probably going to have to do a few steps before it looks anything similar to the right side. So now I'm going to factor, because I have a quadratic on the top. On the top I have a quadratic, but I don't need to do, there's only 2 terms, so I don't need to do trinomial factoring. So I'm going to factor out negative cos theta, because the GCF is cos theta. Okay, so just imagine you're factoring out x. It's x squared plus 2x. You just factor out x. So that's what I'm doing here. I'm factoring out cos x. And then on the bottom, I don't have a GCF, but I'm going to factor out the negative, because I think I'll be able to cross out those negatives, which I will. Gone. So can't cancel anything out yet, because I haven't factored the denominator. So at the denominator, we're going to factor, again, just like we would a quadratic trinomial. Cos theta, should be 2 at the end, not 3. Two, 1, negative, negative. That works. So cos theta minus 2. Wait a second. All right, minus think I made a mistake somewhere. Here, I made a mistake here. So here I factored out negative cos theta, but I didn't factor out the negative from there, so that should have been minus 2. And I knew something was up because once I factored it, I didn't have anything I could cancel out. And if you didn't make a mistake and there's nothing you can cancel out, then that didn't help you. You have to go and try something else. Maybe you have to cross everything out or erase it and start over. So those things will cancel out. Now I have cos theta and cos theta minus 1. Now I'm looking at this, and once you have something that's just cos theta, you can't change it from there. Cos theta is pretty basic. There's nothing else you can change. It's not squared or anything, so it's just cos. I can't really do anything with that. Same with sine. I can't change anything from here. So I think I need to now go to the right side and see if I can get that to be the same. So let's. I'm just going to copy this. Right side. So now I'm going to try to make this equal to cos theta over cos theta minus 1. So let's see what I can do here. I have cos squared theta plus cos theta on the top. So again, I can't do anything with this. This is just the way it is. I could change this to 1 minus sine, but that doesn't really help me. But I have a GCF there. So let me take that out and see what happens. So I'll have cos theta plus 1. And then the denominator, well, that is 1 minus cos theta, right? The Pythagorean identity. So I can change sine squared theta to 1 minus cos squared theta. I can't cancel out yet, but again, just sort of thinking ahead, which comes with practice. This is a difference of squares. 1 minus cos squared theta. Those are two perfect squares, so 1 plus cos theta, 1 minus cos theta, which means these two things will cancel out. They're not in the same order, but they're equal. So cos theta on top. On the bottom, I have negative 1 minus cos theta. So now if I check back in with what the left side I simplified to when I had it there, I'm pretty close. Cos theta on top, cos theta on the bottom. But here I had cos theta minus 1, so it's not quite the same yet. If I distribute that negative in, I get negative 1 plus cos theta, which if I rearrange it, looks exactly the same as what I changed the left side to be. So, again, that was a more complicated example. They can get very complicated. Some of them I've taken up, 2 whiteboards trying to solve. But you just have to practice and practice, because once you do a bunch of them, you'll start to get it, and you'll start to be able to see what's happening on the next step before you actually do it. You can start planning ahead. You also have to be prepared to be frustrated, because sometimes you're going to work for an entire page and then rip it up and start over. So think of it more of as a puzzle than anything else. Trig identities are helpful in calculus for simplifying equations and things, and it's also just, education, exercising your brain. So even though it might seem pointless, and for most of you, the rest of your lives, it is going to be kind of pointless, but it's just sort of exercising your brain, and it'll help you in calculus when and if you get there. Okay, see you in the next one.